Good morning, everybody. Welcome to the third day of the third annual conference of the Mathematics Teachers Association. May I also wish everyone a happy Teachers' Day. The date of Teachers' Day is the reason why we are having the conference right now. So now let me welcome you to our third keynote lecture by the distinguished mathematician Mahan Maharaj. He'll be speaking today on aspects of probability and hyperbolic geometry. Now, our previous keynotes addressed mathematics education and the life of a mathematician. Today, we will get a glimpse of what is happening in mathematics today from one who is playing an important role in shaping it. A very few words about Mahan. Mahan graduated from the Integrated Master's Program at IIT Kanpur and then completed his PhD from the University of California at Berkeley. He then returned to India and has spent most of his time here since. He is the recipient of many honors, such as the Bhatnagar Award and the Infosys Prize. He was also an invited speaker at the last International Congress of Mathematicians. I've been privileged to know Mahan for many years. If there is one thing I have learned about him, it is that he is a breaker of stereotypes and conventions. Moreover, he is also a gifted communicator of mathematics, and I'm sure that we will learn much today. Mahan, hand over to you.
Oh, wow. Thanks, Amber. That's very kind of you. So yeah, Amber was my senior by a couple of years, both in Kanpur and at Berkeley. So yeah, I mean, very good to be back in E-Touch again. And yeah, happy Teachers' Day to all of you here. Yeah, so I got this slightly disconcerting message yesterday saying that this title has scared people. So the thing is, there's absolutely no reason to be scared. This is stuff I've been learning relatively recently. So I think we are more or less in the same boat, and I'll try to share with you some of the things that this topic is about. I'll definitely define what percolation is. I'll say what hyperbolicity is, and I'll say what hyperbolic groups are. And then we'll try to assemble these pieces together. So as Amber said, the topic of this talk actually is at the interface of two classical subjects, group theory, geometry on the one hand, and probability on the other. So this word percolation comes from probability, and I'll say a little more about it, but let me say right at the outset that it started off as a model for how fluid flow is. I mean, it's a model for fluid flow in a discrete setup along, say, graphs. So say you have a bunch of pipes all connected together, and how liquid flows along those pipes. So that's all that. I mean, it's a very simple-minded model. I'll say a little more about it. So there is some randomness involved. And the right side, hyperbolicity, it comes from geometry. And so if you put this randomness and geometry together, you get this emerging area of mathematics called random geometry. Yeah. So yeah, so that's all it is. So essentially, what exactly is random geometry about, and how are you going to talk about it in some sensible way, is what this talk is about. Okay, and whatever new I'll be talking about in this talk is all joint work with Riddhi Pratim Basu, who's a probabilist, and I would like to pass myself off as a geometer. So he's the probabilist, I'm the geometer, and when you put a probabilist and a geometer together, you get some random geometry. Okay, so now let's get on with this. So what is yeah, okay, good. So as I promised, yeah, that's correct. So yeah, so in case you're not using your mic to ask. So by the way, feel free to ask questions at any time. And Amber, since my chat is not open, it will sort of keep obstructing things. Can I request that if there's a question, can you just sort of interrupt and yeah. And
Sure.
please, yeah. So if there's any mathematical question, please feel free to just interrupt without typing it in. So yeah. Anyway, so the first part of it is asking what exactly this percolation is. So where does the randomness, the probability come into the picture? So what do you start off with? You start off with a graph. So this V is the vertex set and E is the edge set, and the two together give you a graph. That's the underlying, so the graph comes typically equipped with a standard way of measuring distances. What is that? It's essentially you assign length 1 to every edge. And so any path, you just count the number of edges that are there in that path, and that's going to give you maybe with multiplicity, and that's going to give you the length of the path, right? So that's a very naive way of counting, but it still gives you a distance in the sense of a metric space. Now, once you have that, and with some very mild conditions, so assume that the valence or the number of edges coming out of every vertex is uniformly bounded. Then by a simple diagonalization argument, you can always ensure that any 2 points are going to be joined by at least one shortest path. So which means that the distance can be defined by looking at the minimum and not just the infimum, the minimum of the number of edges joining in a path which joins point A to point B. Yeah, so that gives you a distance. So a graph, though it looks a priori like a combinatorial object with no extra structure, it comes naturally equipped with a metric where you assign length 1 to every edge. Okay, now here's where we are going. I mean, this is the point at which we are going to introduce randomness. The edge length 1, bear in mind, is the deterministic geometry underlying the random geometry that we are going to be talking about. Yeah. So this graph is a model of deterministic geometry. Now we want to introduce a little more of randomness into the picture. So what we do, we assign a probability distribution on R plus. So for technical reasons, I have allowed infinity. So each edge has length varying between 0 and infinity. If the length is infinite, then what it really means is that you've removed the edge and liquid does not flow along that edge. Yeah. So that's what this is. So what does this probability distribution really encode? It encodes a probability distribution on lengths of edges. So R plus is a length. So instead of assigning deterministically every edge length 1, you allow the lengths to be arbitrary positive lengths. And the distribution of these lengths is according to a probability measure on all of R plus. Yeah? That's what it is. And it will not be as general as that, because for most practical purposes, at least for the purposes of this talk, the kind of model we'll be really interested in is where the probability distribution is continuous. So think of some continuous function, positive continuous function on the positive real line, yeah, whose integral is 0, whose integral is 1. So that's a probability measure. So so the probability distribution function is given by rho, its integral is 1. Okay, fine. And now we want to say what the probability measure space, the total probability measure space corresponding to this gamma is about. And here it is. So you look at, I mean, if you assign lengths arbitrarily, what are you really doing? You're just getting a function from the edge set, well, this block E and that curly E are the same. So I've changed fonts a little bit, but yeah, so E and E is equal to E. Yeah. So this E here and this E here are the same. So what are we doing? So what is an assignment of lengths? It's just a function from the edge set to the positive reals. Yeah. So when you look at the probability, the total probability space encoding all possible lengths, so what are you doing? You're really looking at R plus equipped with the probability distribution taken with itself, a product measure. That's what you're really looking at. And you look at R plus comma rho and take a product with itself, cardinality of E many times. So gamma will typically be, it might be, and in this particular talk, it typically will be an infinite graph. So it's really a product of infinitely many probability measure spaces. So that's a probability measure equipped with, say, the product sigma algebra, etc., etc. The standard product measure is what we are talking about. What does that immediately tell you? It basically says that once you've taken this particular probability measure, it means that what length you assign to one edge does not in any way say anything about what length you assign to a different edge, which means that this assignment of lengths from this total measure space capital omega, the assignment of lengths to different edges are independent events. One does not influence the other in any way. Formally, you can think of this assignment of lengths as a function on the set of edges. What does it do? It eats one of these points of this probability measure space. Little omega is a typical element of capital omega. So it eats an element of that and spits out exactly the length of E. So capital X sub E is a random variable. It's a measurable function on the total probability measure space, which eats a function or an element of this product space and spits out the length of E. Yeah. So that means what? The edge length, the length of the edge E is something that is not deterministic at all. It's parametrized by this probability measure space omega, right? So length has now become a function. It's not deterministic one as in the gamma case that we started off with, but it changes according to which point of capital omega is being used to sample. And then so once it's a random gadget, it'll have to follow a certain probability law. And that law is given by this probability distribution rho. Yeah, that's the meaning of all this. Fine. So now, so when we say that we have assigned a random length to a geometric object, in this case, the length of E, what we are really meaning is that there's a fixed geometric object, in this particular case, the edge E, and the length of that is some geometric output, which is now parametrized by this probability measure space capital omega. So what is random geometry? This is a slogan that you could carry back with you, even if the rest of the talk puts you to sleep. What you really should carry back with you is random geometry is geometry parametrized by probability. So geometric objects are measured, and those outputs, those numerical outputs, the lengths, or maybe even a geometric gadget, namely a geodesic, once you have geometry parametrized by a probability measure space, in this particular case, capital omega, what you have as an output is random geometry. To repeat, the parametrization space is what gives you the probability, and the object that you are parametrizing is geometry. Yeah, so essentially, if you want to think of it in some sophisticated language, this really is the same content. It's essentially a bundle of these where the fibers are graphs, and the base space is the probability measure space. So again, geometry parameterized by probability. That's what all this is about. Okay, fine. So we started off with one particular object, one particular geometric object parameterized by probability. What is that? Length of a fixed edge. Yeah. So length is a geometric object parameterized by the probability space. That was the first simplest prototypical example of a random geometric object. Now, once we've done that, we are really in a position to start off doing a lot more. Instead of a single edge, you can fix an edge path. Yeah. So in your graph, now you don't assign lengths, it's just a sequence of edges. So what will an element of the total probability measure space do? It's going to eat this edge path, little gamma. And what is it going to spit out? It's going to spit out the total length of gamma, which is obtained by omega of the edge, summed over all the edges belonging to that edge path. Okay. So now, once you've found a way of assigning a random length. So every time I say a random object, it's not a fixed object. It's a geometric object, again, parameterized by this space, capital omega. Yeah. So if you, once you've assigned random lengths to all edges, you can immediately assign random lengths to finite collections of edges. What do? You just sum those lengths. So each omega is going to assign a length e, sum over all the edges belonging to this gamma, and then you have a length of that path corresponding to little omega. Let little omega vary over capital omega, and you have lengths of gamma parameterized by your probability measure space, capital omega. Now, once you have that, then you can take the infimum. Once you get the infimum, then for each little omega, what are you doing? You can assign a distance to any pair of points. So the first random object we looked at was a random edge. The second random object we looked at was a random edge path. Now we are looking at random distance between a pair of points. So what are we going to do? You look at all possible edge paths gamma connecting x and y, and you look at the infimum of all these lengths as little gamma varies over all paths connecting x and y, and you get a distance. But this distance, d sub omega, corresponds to the particular point, little omega, in your probability measure space. You let little omega vary over capital omega, and this d omega now becomes a function of little omega. You have take as input x and y, and d omega varies. So you have a random distance. So x, in this particular case, gamma, equipped with a metric, is a metric space. But now the metric, which is something that assigns lengths to, that assigns distances to every pair of points, certainly the symmetry holds and the triangle inequality holds. There's a little subtlety about whether d omega xy equal to 0 if and only if x equal to y. Under very, very mild conditions, even that holds. So this really, for each little omega, you really do get a distance on your graph gamma. So what we have as an output, you have for every little omega belonging to capital omega, you have a metric on your graph gamma. It's no longer this boring metric that we started off with, where every edge has length 1. Now that metric fluctuates. Yeah? So when little omega varies over capital omega, you just get a family of metric spaces where the underlying space is exactly the graph gamma, but the distance changes from point to point. So that's the random distance. So we have a random metric space. We'll call gamma equipped with this family of metrics d sub omega parameterized by capital omega, a random metric space. So that's this random talk again. Yeah. And here's this. Okay, so this letter, I had no idea what this letter was called. Apparently it's called epsilon. So anyway, so this epsilon xy, what does it do? It not only so as I said, you not only have a distance, but the distance, the infimum, is actually realized under very mild conditions. So which means that not only do you have a number, you also have a bona fide, a genuine geometric object. What is that? That's the actual path. That's the actual path which realizes this distance. So you might ask whether this path is unique or not. Well, I had said at this, earlier, that little omega belongs to this probability measure space, and the probability is a continuous probability. So if you have a continuous probability, the chance of two edge paths having the same length is really zero. Yeah, and there are really countably many paths between 2 points, so you need not bother about it. So basically, in this random world, geodesics are typically unique. So with that sort of heuristic, this distance, the random distance between a pair of points is really realized by a unique path. Yeah. So what does it give you then? Every little x comma y, you eat a point from the probability measure space, capital omega, little omega belonging to capital omega. And what do you spit out? You spit out both a distance and a path realizing that distance. So which means you have a distance minimizing path, also called a geodesic. Now this geodesic from point to point might change. The underlying edge set might change. So you really have a geometric object that changes from point to point. So this is what we shall call a random geodesic. Now, this particular model where all the edges are IID, which means they are independent and identically distributed according to the probability distribution rho, this particular model is called FPP, or first passage percolation. This is a model of random geometry. So let me say why it's called first passage percolation. So think of your floor tiled by square tiles. And then at some point, you allow liquid to be dropped at a particular point. And then you allow the liquid to flow along the cracks. And so you fix your origin, fix the point where you stand, and do the splashing of water any number of times, and see how long it takes for each of these experiments for the water to flow from point 00 to point 100, 237. Yeah. So different experiments are going to, because the exact resistance along various of these cracks is not some deterministic object. So liquid is going to flow at random along the cracks. And then you are going to get the different passage times from your origin to this point 100, 237. And what is it going to give you? It's going to give you basically a probability distribution on the distances, yeah, on the amount of time that liquid took to flow from the first point to the last point. And since it's the first time it reaches the last point, it's called first passage. And why is it percolation? Because liquid or any gas, for example, is what percolates. That's why it's called first passage percolation. And this was formulated long back, somewhere probably in the 50s. And the time that you take, which is this distance, this random distance. So think of random distance as parameterized by little omega as eating x, y, and spitting out the distance. Or you can think of it, fix the pair of points and then eat a point in the probability measure space. So depending on which you regard as the variable, so Txy omega is the same thing as d sub omega of xy. T sub x, here the point is that you think of T of xy as a function of omega with x and y fixed. You think of d sub omega as where omega is fixed at x and y values. It's the same quantity once you have omega and x and y matched up, but depending on your point of view, we have two letters. So Txy omega, this is called the first passage time between these 2 points, x and y. So as I said, Hammersley and Welch, those are the names. They formulated this as a model for random fluid flow way back in the 1950s or thereabouts, or maybe a little later. And it's been widely studied, particularly for the plane for Z mod 2, to an extent for Z mod 3, and then to generalize to Z mod n is not so difficult. So what is Z mod n? not z mod n, z to the n, or z square or z cube. What is that? It's essentially z square is essentially the square grid in yes. Somebody wanted to ask a question. Please go ahead and, as I said, yeah, you can. Somebody had raised a hand. Somebody called Dinesh. Do you have a question? Oh.
So right now the hand is not raised, Mahan. So I guess it will be by mistake.
Pardon me?
Right now I don't see a raised hand. So maybe it was by mistake.
Okay, fine. Okay. All right. So what is Z2? It's basically the standard grid in the flat plane. Yeah. So think of all the it's basically say a standard net, yes, with square holes. Yeah. So think of each of the vertical and horizontal edges as edges of your graph, and the vertices are your vertices of the graph. So that standard two-dimensional grid is the graph corresponding to Z2. And if it's a three-dimensional mesh with all the coordinates perpendicular, with vertices at points with all integer coordinates, that's your Z3 inside R3. Yeah. And now you can do the same thing for n, Z4, Z5, etc. And so this particular model, this is basically what is called Euclidean first passive percolation, has been widely studied. The thing is, so I was reading, I should mention this. There's this wonderful book by this, perhaps the last universal geometer, Misha Gromov, called Great Circle of Mysteries, Mathematics, the World, Mind. So very grandiose title. And essentially where he sort of quotes Poincaré to say that essentially Poincaré had come up with this explanation, tentative, probably speculative, as to how the human brain takes in as our input the external world and outputs Euclidean geometry as the model of geometry of the space which we live in. Yeah. The point is the Euclidean geometry that we see around us is really a product of our brains. Yeah. Well, that's actually the real point. Yeah. Anyway, but if we probe a little deeper, essentially challenging the brain to give up its old habits, then we see that actually Euclidean geometry does not have anything particularly sacrosanct about it, yeah? Except that we are accustomed to it. So why Euclidean geometry? And once that question is asked, you can have any geometry of the graph. So the background graph gamma could be any graph you like, any graph. At least for the time being, just let's impose some upper bound on every valence, say 10,000. So every point has valence bounded by 10,000. That's good enough. So what are the geometries that you're going to get? And so this brings us to the next point in our talk. So next slide, really. Here, what we'll do is we'll forget the probability, get back to the deterministic geometry underlying a graph, and try to understand what hyperbolicity means. Hyperbolicity, let me say, from the reason why one is interested in is that is basically because if you throw away the Euclidean prejudice, then a random geometry, well, not a random geometry, the correct thing is that a typical geometry of a graph in a certain pretty precise sense is really hyperbolic. So our brains sort of trick us into taking this very special kind of geometry, namely Euclidean geometry, but a typical gadget in a very precise sense is really hyperbolic. Yeah. So what is hyperbolic geometry about? That's what this slide is. So let's get back to the deterministic setup again. So it's what is our probability distribution? It's a Dirac mass supported at the point 1, which means what? Every edge has deterministic length 1. No probability, no randomness. Okay, fine. But to be,
Mahan, sorry
yes,
to interrupt. Yeah, there was a
no, go ahead.
question in chat
Yeah,
from Jam actually, and he asked that like we have a Euclidean mapping of the plane, is
yes.
there a comprehensive or canonical view of random 2D surfaces?
Ah, yeah. Well, so here is the, okay. Thanks, Jam. Lovely question. So um, the correct answer is, I mean, okay, so I'll give you the first, which is technically correct, but very boring answer, which is that you can't quite picture a I mean, there is no fixed surface. Each fixed surface is typically going to be a probability zero event. Yeah. So really, if you want an authentic picture, what you really need to draw is an uncountable infinity of surfaces. That's impossible. I mean, again, I mean, because I mean we are accustomed to thinking of countably many things. So the boring answer is that really it's impossible to a draw a random geometry, because there are, I mean, it's like drawing, say, infinite family, where that infinity is uncountable family of graphs. On the other hand, what you can do is, say, basically pick out, I mean, if you have a probability distribution on these surfaces, or etc., what you can do is pick out one guy around which the probability distribution has some positive measure, say it's concentrated. So essentially, if you ask, and this is a more interesting interpretation of your question, so what does a typical guy look like, so that you can have some visual input about it? And the answer to that is yes. And one can do that, but it looks very, very fractalish. Yeah. I mean, so for example, there's a different model, and this is something for which there are pictures where computer simulations play a big role. So basically, think of the sphere, just the round sphere. So I'll divert a little bit away from this. Yeah, maybe I'll come back to this question at the end, because this is going to take us a little away from the central theme of the talk. So is it okay if I come back and address this? What is a typical random geometry? What does it look like once
Yes.
this is done?
Yeah, I think that's a good idea.
Yeah. So, and I'll probably, by then I'll try to hunt up some. I mean, there are pictures on the internet which you can look at, and it looks pretty crazy. Okay, fine. So let's get back to this deterministic part of what constitutes hyperbolic geometry. And as I said, so the graph now is equipped with the standard deterministic distance, where every edge has length 1. So how do we introduce hyperbolicity on this? We want a little extra symmetry. Yeah. Excuse me. So Z2 or Z3, it's not just an approximation of the Euclidean 2 plane or the Euclidean 3 space where we live. It has an extra structure. It has a structure of a group. So basically, you translate forward, backward, or top, bottom, or third coordinate. Those translations are there, and those guys leave the graph invariant. So this collection of symmetries can be captured in the structure of a group. In this particular case, that group itself is Z3. You just look at pointwise addition and subtraction. Yeah. So that's your binary operation. That group acts what is called transitively. Vertices are taken to vertices, and all vertices are covered. So that's your group. So we want this extra symmetry for largely for aesthetic reasons and for mathematical reasons, because these are typically some of the most interesting structures on these graphs. So that brings us to the notion of a Cayley graph. So this was done by the mathematician Cayley around end of the 19th century, early 20th century, maybe end of 19th century. What do? You have a group G, arbitrary finitely generated group, with S a finite generating set. What does that mean? It means that you look at the group generated by S, inside this finite set S inside a given group G, and the group that those finitely many elements of the group generate is the whole group. So you are allowed to take multiplication, inverses, and you look at the entire set, the transitive closure of all this stuff, and you get the whole group back. So that's what is called a group G, but it's now equipped, it's decorated with this extra piece of information, namely a finite generating set. How out of this? So what are the examples? Just look at Z as the group, and then this S, the set S, is typically going to be assumed to be symmetric, which means that if little g belongs to S, we'll also assume that G inverse belongs to S. This is for aesthetic reasons. It's not very important, but it's good to have it in mind. So for example, if you just take Z as your group, just look at the element +1 and by symmetry also -1. So that's your generating set S. So what's the Cayley graph? The Cayley graph has as its vertex set all the elements little g belonging to the group G. Yeah, all those guys are vertices. What are the edges? The edges consist of pair of group elements such that they are connected by one of these generators. So G inverse H belongs to the generating set. So the difference between two vertices, if it belongs to the generating set, if and only if it belongs to the generating set, you connect the two vertices by an edge. So you get a graph. All right. So simplest example, Z, take +1 and -1 as your generating set. So 0 and 1 differ by +1. So you join them by an edge. 1 and 2 differ by +1, join them by an edge. 2 and 3 differ by +1, join them by an edge. 0 and -1 differ by an edge, so join to -1. -1, -2 differ by -1, join by an edge. And what do you get? You get back your real line. That's your underlying space where there are vertices at every integer point and edges between successive integers. Now, nobody has told you that, okay, you have to choose +-1. So here's a nice exercise. What happens when if you look at the generating set as +-1 and +-2? Certainly +-1 generates, so +-1 and +-2 also are going to generate your full group Z. Now what do you get? You really get a strip. Yeah, it's basically an infinite rectangle which is styled by equilateral triangles. So there's 0, so basically you put +1, +3, +5 on the top line, and -1, -3, -5 also on the top line, and the bottom line has all the even integers 0, 2, 4, 5, 4, 6, etc., etc. And 0 is connected to 2 because +2 is in your generating set. 2, 4, 6, all these guys. Now there's a copy of the real line there. There's a copy of the real line at the top, and they are connected by sort of equilateral triangles. 0 goes up to 1, 1 comes down to 2. So 0, 1, and 2 are really now vertices of a triangle, and then the triangle flips, and you have -1, +1, and 0. So you have a triangle which is vertex at 0 and base at -1 and +1. And then you flip again and so on. So you get a thin, long, infinitely long strip tiled by triangles. So that's the edge set of that is your Cayley graph of Z again. But now when you change the generating set to +-1, +-2. Okay, fine. So that's an example, 2 examples of Cayley graphs. Now we're going to say where hyperbolicity comes in. So now note that this thing here does not have any local structure. A geodesic metric space is delta hyperbolic if for all x, y, z belonging to the space, to the geodesic metric space, the edge joining, so this box x comma y is the notation we'll use for a geodesic. Yeah. So you take any edge joining any geodesic path joining these 2 points x, y. So x, given 3 points x, y, and z, you can construct a triangle. Join x to y by a geodesic, x to z by a geodesic, y to z by a geodesic. So you have these 3 sides of the triangle: x, y, x, z, and y, z. Yeah. When is a space hyperbolic? if there is, it's a space is delta hyperbolic, delta could be some very large number. Yeah. So typically in mathematics, we think of delta as small numbers. Here you can think of delta as some arbitrary large number. Yeah. So basically say 1,000,000. So each edge of the triangle, which is, well, each geodesic, each side of the triangle is contained in the delta neighborhood of the union of the other two sides. Okay. That's what hyperbolicity is about. So what are typical examples? So typical examples say are trees. Yeah. So the thing is, these natural examples that we see around us are trees. And this kind of geometry is something that emerges automatically. Yeah. There is no smooth structure. A tree goes up and then branches off. It goes up and branches off, etc., etc. Yeah. So for example, I mean, you model the tree by, say, every branch, say, assign it some fixed length. So what happens? What does a triangle look like? So you take 3 points, then the triangle is just going to look like a tripod. Yeah. So each edge is actually contained in the union of the other two edges. So if you have, say, 3 points on a tree and you join them up by the shortest path, then what are the union of the shortest paths? What will they look like? They look like some Y or T, the English letter Y or the English letter T. So each edge is actually contained in the union of the other two sides, which means that it's contained in the zero neighborhood of the union of the other two sides. So delta is zero. A zero hyperbolic space is a tree. Yeah, that's a mathematical definition of a tree. Okay, fine. So now we've defined two things. One, a Cayley graph corresponding to an algebraic object, namely a finitely generated group. And we've defined a geodesic metric space, which is a general background geometry. Time to put these two structures, G. So now we are calling an algebraic gadget, namely a group, and we are giving it a geometric property. We say that it's hyperbolic if a Cayley graph with respect to some finite generating set is hyperbolic, which means it is delta hyperbolic for some delta. Delta could be 1,000,000, could be 10, could be 0, could be 100 million, anything but a fixed number. The point is that the Euclidean space is not hyperbolic at all. Give me a delta, say 10 million, I'll construct an equilateral triangle of size larger than that. So basically take a equilateral triangle where the edges are of length. If I give you 10 million, just take 100 million, yeah, and take a Euclidean equilateral triangle, and you will see that no side is contained in the 10 million neighborhood of the union of the other two sides. And so this is going to be true for any n, which means that Euclidean two-dimensional space is not hyperbolic. Yeah. So, but these groups are really ubiquitous. Yeah. So the problem then becomes, how are you going to study this random in this background geometry of hyperbolicity, which is a typical background geometry? How are you going to study this randomness? How are you going to impose randomness now not on a background Euclidean geometry, but on a background hyperbolic geometry? That is the problem that we are going to be looking at. So yeah, I mean, I've spent, I think, 3/4 of an hour essentially explaining what this talk is, I mean, what this stuff is about, but that it really helps here, because we are really taking two ingredients from two well-respected areas of mathematics and trying to put the two of them together. So here are models. So for example, let's start with the stuff at the bottom. This is an example of a Cayley graph of what is called a free group. So what is a free group? Just look at A and B as your generators, throw in A inverse and B inverse by symmetry, and you look at all words where there are no cancellations. Yeah, A is not followed by A inverse, B is not followed by B inverse, or the other way around. Yeah. Now what are you going to get? You're going to get a regular tree where every vertex has valence 4. That means 4 edges coming out of it. they are labeled by A, B, A inverse, and B inverse. Yeah. And similarly, when you go to A, you can come back to identity by following A inverse, or you could go top by AB, down by AB inverse, and forward to A square. What you get is this regular 4-valent tree. And note that the boundary of that is now looking more and more like something that's self-replicating geometry. So that gadget is what is called a Cantor set. It's an example, it's the simplest example of what is called a fractal. And this is a certain certain inevitable thing that emerges from hyperbolic geometry. There is a boundary, and you can see it in the crinkly surface structure of trees. Yeah. And in nature, every time one is solving a maximization of surface area problem, the geometry that results is hyperbolic geometry. The trees are trying to maximize the surface area of contact with the sun so that they can manufacture more food. Yeah. And our human brain is, the prefrontal cortex, it's trying to multiply its divisions so that there's a huge amount of interconnectivity. So every time you try to sort of explode and maximize interconnectivity, you do get this huge amount of structure. Yeah. Similarly, on the left side, there is on the two fellows on the top. I won't dwell on the first picture too much. The second picture is basically a skeleton of one of the models of a painting by Escher, Maurice Escher. So this is a tessellation of what is called the hyperbolic plane, where you're really tiling everything by triangles, where the angles are pi by 6, pi by 2, and pi by 4. Yes. So pi by 6, pi by 2, pi by 4. Please note that the sum of the angles is less than 180 degrees. This is how classically hyperbolic geometry was discovered. It was really discovered by Gauss, but he did not publish. And really, so it's attributed to Bolyai, a Hungarian mathematician, and Lobachevsky, a Russian mathematician. But this is, it's really due to Gauss. And equivalent formulation is that the sum of the angles of a triangle is less than 180 degrees. And then what do you get? What is the fractal? The fractal is the boundary circle. Yeah. So every hyperbolic group then comes equipped with a natural boundary. And I think in the last 10 minutes, I'll try to say a few things about what we got as an output of our study of this particular kind of random geometry. As we said, this has been studied for 60 years or so with a Euclidean background, but what are the new kinds of features that come in when you study it in this background, typical geometry, namely hyperbolic geometry, and you really get a lot of new stuff. Yeah. So first thing, as we pointed out in the last slide, a key feature is this boundary. So what's the good thing about having a boundary? Here is the thing. In a graph, there is no continuous way to parameterize directions. Yeah. So here is the point. Here is the point. So here is the point. So if you have a Euclidean structure, say if you have R2 or R3, or more generally what is called a differentiable manifold, you can take the tangent space at a point. So that's an infinitesimal gadget. So that gives you a parameterization of the various directions at a point. So that's actually a vector space. But in a graph, you have just 3 edges coming out at a point. So there's no real point in talking about a tangent space. On the other hand, there is a way of parameterizing directions. Instead of looking infinitesimally, you look at infinitely long geodesic paths. So the collections of geodesics and really their asymptote classes gives you a boundary, but not at a, so it gives you a way of parameterizing directions, not at a point, but at infinity. So we invert our viewpoint, and instead of thinking of directions as some infinitesimal thing, think of them as parameterizing stuff at infinity. And so you use this boundary to parameterize directions. This is a crucial feature of this graph as encoding geometry. And really, we have to switch from infinitesimal to at infinity. Now, this comes equipped with a natural measure, another natural probability measure, but which is completely, it has nothing to do with what we were talking about. So there's a new measure, new, yeah, pun unintended, on this boundary, which is really a weak limit of uniform measures on balls of radius n. Yeah, so basically take a ball of radius n, equip every point with an equal mass, and let n tend to infinity. So you're going to get a collection of probability measures, and there is going to be a limit, a sequential limit. This gadget is called the Patterson-Sullivan measure. And so once you have this boundary equipped with a probability measure, you can start doing measure theory on it. So when you parameterize directions and we say almost every direction, it really means almost every direction with respect to this particular Patterson-Sullivan measure. So just to emphasize, when we say almost every with respect to geodesics or random objects, we are parameterizing by this parameterization space capital omega p. But when we say almost every direction, we are parameterizing with respect to this Patterson-Sullivan measure. Yeah. So there are two different probability measures in the game. One comes from hyperbolicity and has nothing to do with the parameterization space. The other is coming from the parameterization space. So now we can parameterize directions, and I think I'm in a position to state the first theorem. So here's the point. A deterministic geodesic gives you a direction, hits the boundary at a fixed point. Now, the first question that we ask is, okay, fine, this is a deterministic thing. How far off is a random geodesic? Now we allow the geodesic to be changing according to our parameterization space, which is our probability measure space. How does it change? How does it give you, I mean, does it, is it allowed to accumulate on more than one point? Certainly you can draw paths which accumulate on any number of points that you like. If you like, you can have a path which accumulates on the whole boundary. But what about random geodesics? Those are, I mean, how far off are they in terms of this? And so for that, we'll really have to define what it means for a path to accumulate on a boundary point. And you say that a path sigma starting at a point O has direction xi. Xi is now thought of as a point on the boundary. If the only accumulation point in the boundary of sigma is this point xi. Yeah, this is the best we can hope for. So if we'll say that a random geodesic, which is a priori just a path, it accumulates at a single point is the best we can hope for. And the answer is yes, it is true. You take any xi, any point on the boundary, and let a sequence, just take arbitrary sequences x sub n converging to that point xi. Then for almost every point in your sample space, you look at the sequence of omega geodesics. So now you're fixing little omega and you're looking at the random metric space parameterized by little omega, and you look at the geodesic segment in this omega metric, 0xn with respect to omega, and you look at it as xn converges to xi. This guy converges to a ray 0 xi omega, and its direction is xi. What's the takeaway? Sure, deterministic guys have these deterministic geodesics which converge to xi. The same thing is true for random geodesics. They do not wander too far off. They do not go off and make friends with some other point on the boundary and accumulate towards it. If you take points on your geodesic going off to xi, and then you allow your omega, little omega to vary, then for almost every little omega in your parameterization space, the accumulation point of the random geodesic is this unique guy xi. Yeah. So random geodesics at least asymptotically, what sort of a colloquial way of saying this, random geodesics asymptotically behave like deterministic geodesics. That's the output from this. Okay, good. Now, so we've got direction. So now how about quantifying this? How about making this more precise and getting a precise number out of this gadget? And as I said, there is a way, there's a random time of passage, namely this random variable Txy omega, which eats little omega belonging to the capital space, the probability space capital omega, and spits out the distance. Yeah, spits out the amount of time you require to pass from x to little y. Fine. Once you have that, you have the x. I mean, yeah. So once you have a random fellow, you can always integrate it out with respect to the probability measure and get the average. Yeah. So there's an expected passage time from little x to little y. Okay. Fine. So then how are we going to, so we have that almost every random geodesic does have a direction, but how are we going to give that a number, assign a number to that? So what are we going to do? We are going to basically look at expected random time divided by deterministic distance. Yeah. So given xi belonging to boundary G, define the velocity in the direction of xi to be the limit as n tends to infinity, expectation of the random time from O to xn. So basically that's the average on the numerator, yeah, divided by the deterministic distance d from O to xn, and now let xn tend to infinity. Now let n tend to infinity. Yeah. So basically you take x sub n's along the deterministic geodesic, you look at the rand and take a point on that geodesic, which is that time distance n deterministically from the origin. Look at the random time, so as the random distance, average that with respect to the probability distribution, that gives you your numerator. Divide out by the deterministic distance d of O to xn, which in this particular choice is just n, and now let n tend to infinity. This we are going to define as the velocity. Well, yeah, it's all very well to say that we are going to define this to be velocity. Who has told us? Nobody has given us a guarantee that this limit exists. So this is called the velocity provided the limit exists. Yeah. So if the limit exists, then the notion of an expected passage time or a velocity, and we've been very cavalier here, we've called this velocity, it's also called the passage time constant. We've been cavalier because we basically overturned the physicist convention of distance by time as velocity. We've called time by distance velocity. Anyway, mathematicians are reputed to be cavalier, have no sense of what is appropriate in the real world. So we've carried on that glorious tradition here, and we've called time by expected, the random time. Think of it as random distance expected divided by deterministic distance, limit as n tends to infinity. That's the velocity provided the limit exists. So now we'll introduce a little bit of an assumption on the probability distribution. So Amber, I started, I think, 5 minutes late, so I'm taking a couple of more minutes. Is that okay?
Yeah, that's fine, Mahan. I think we have.
Yeah. Okay. So, so now we sort of assume a little bit of, so we impose a little bit of an assumption here on the probability distribution. Firstly, it's a continuous guy, so it does not have any atoms. Atoms mean there is no concentrated mass at any point. And suppose it is sub-Gaussian. This is what, so what is sub-Gaussian? It means that there is some a greater than 0, and you look at the expectation of e to the ax square, yeah, then e power ax square has a finite mean, yeah. That's what is called sub-Gaussian. Yeah? So it looks like e power minus x square. That's what it's called, sub-Gaussian. So this assumption we just thrown in, this is not the most optimal guy. There are much easier fellows, but we are not interested in the analysis. We are really interested in the geometry here. And here's the statement: for almost every point in the boundary, the velocity v of xi, which means that this limit does exist. And so here's the point. Let me stress this. for almost every point in the boundary, the velocity in the direction of xi exists. What I am asking you to note here, it's only true for almost every. Yeah, we made the statement for a reason. The next is that this velocity that we get is actually constant in almost every direction. So that means independent of the direction, the velocity is constant. It exists and is constant. Now, going back to the point I stressed, I've said almost every, even for the free group with some slightly cockeyed generating set, you cannot upgrade this almost every statement on the boundary to every point on the boundary. So this almost every is part of life, part of the way nature behaves. It's part of the way hyperbolic geometry interacts with random geometry, with probability. You cannot upgrade this almost every statement to every. First. Second point is this constant. Yeah. These are both these points are very different from the way Euclidean random geometry or Euclidean first passive percolation on Z2 behaves. There, the velocity does exist under very mild conditions in every direction. So it's not almost every, it's genuinely every. One. Two, and it's very far from constant. So these two differences really arise from the way the group, so this boundary, so even the Euclidean Z2, it has a collection of asymptotic directions. Namely, it's parameterized by a circle. So just look at theta. Theta gives you all the directions of the geodesics going off to infinity in R2. But what does the Z2 act on it? I mean, any straight line, you act on it by any isometry. What is it going to do? Any orientation preserving isometry, this translation given by these translations. So you translate a straight line, it's going to be translated to another line which is parallel to itself. So the action of Z2 by translations preserves asymptotic directions. So on the boundary at infinity, the Euclidean Z2 acts by fixing every direction. That is very different from the kind of action on the boundary that arises in this hyperbolic situation. In the hyperbolic situation, it mixes all directions. The formal way to say it is that it's ergodic, which is a very precise way of saying that no direction is preferred. There is no invariant. I mean, so all the directions, any direction can be taken to effectively any other directions in a precise probabilistic sense, in a precise measure theoretic sense. So which means that if you have velocity, so this velocity is a measurable function, if you act on it by the group, it turns out to be an invariant function. So you have a function on the boundary which is invariant by a group acting on it. And this is really the definition of ergodicity. Ergodicity basically says that the only function that is invariant is the constant function up to measure 0 sets. So again, two things, velocity is constant, very different from Euclidean geometry. One. Two, it's really almost every, so it's a measure theoretic statement, not a topological statement. This also is very different from Euclidean geometry. So these are two things, and there's a couple of other things, but I think right now I'll stop in the interest of time. And yeah, thank you very much.
Okay, thank you so much, Mahan. That was really fascinating. We do have a couple of questions in the chat. I also wanted to ask you, these exceptional directions, the ones that are getting left out of it almost every, can we see them in the pictures that you have gone, like maybe in that green thing?
Okay, so here is, so I haven't quite, so the thing is, yeah, actually it's a basic, there's a, yeah, okay, this is the picture. So here's the point. In the free group with this particular generating set, you can't see them because they don't exist. Why? Because essentially the random geodesic is always the underlying deterministic geodesic, because there is no, I mean, you're not allowed to go to a path and come back, right? So that's just going to add length. So it's not, so the in any random geometry, in any probabilistic model on the free group, on this tree, the deterministic geodesic is the underlying set of any random geodesic, because you can't have a path being retraced. So you can't quite see it on this tree. However, I did mention at some point of time the Cayley graph of Z with respect to this slightly strange generating set, namely ±1, ±2.
Right.
What does that tell you? So it basically says that to go from the point 0 to a point n, you have more than one path. You have actually zillions of paths, which means somehow or the other, the amount of time, this is some heuristic which can be made precise, the amount of time that you'll require to go from point 0 to point n becomes faster in this metric, in this graph with more edges attached, because you have different paths for the water to travel. Okay, fine. So now you interbreed these two guys. So on the A side, you keep the original metric. So, and on the B side, you introduce generators plus by both B and B square. So B square, B inverse, B to the -2. So in the B direction, the flow is faster. In the A direction, the flow is slower, which means that the velocity in the direction A to the infinity. So A to the infinity is just this straight line going off to the end towards plus infinity along the x-axis. B to the infinity is going up towards plus infinity in the y direction. So the velocities in these two directions will be different. If along the B direction you put in more edges, and on the A direction you don't introduce any extra edges so far. Okay, this is step one. So basically says that you can manufacture directions by cooking up your generating set so that two directions have different velocities. Step one. Now we'll construct a path by hand, and I'm sure that you can't quite see it on that picture. It's difficult to draw, but I'll just sort of tell you the labels of that path, and you'll immediately see that, yeah, that's how it is. So you look at the word which is given by a power 10, followed by b power 10 power 10, followed by a power 10 power 10 power 10, followed by b power 10 power 10 power 10 power 10, etc., etc. So it's this tower function, and the power of it is 10. The next fellow, the power is 10 power 10. The third fellow has power 10 power 10 power 10. The fourth fellow has 10 power 10 power 10 power 10. There's a very wasteful way of constructing, but it makes it transparent. What happens is that the new term completely dominates all the other fellows to any degree of approximation that you like, which means what? Up till the nth time, the dominant term is the A direction. Say if the nth term is a power some tower of tens, then the velocity at that nth term is going to be determined basically very close to the velocity given by the velocity in the direction of a to the infinity. As soon as you switch to the next guy, what will happen is the velocity is going to come back to the b power 10 power 10 power 10, because that's now going to dominate. So the velocity keeps oscillating between two values, which means that the limit does not exist.
Yeah. Yeah. Okay, let me share a couple of the questions from the chat. So Akhlaq Hussain has asked whether the random geodesics will satisfy similar properties as geodesics in classical geometry, and is it possible to characterize more randomness in nature using these random geodesics?
Yeah. So what exactly? I mean, yeah. Could you just come? I mean, is it okay if he comes online?
Yeah,
and
sure.
sort of spell out?
Akhlaq, you can just speak and
Unmute and basically clarify what exactly do you mean by what are the yeah.
Hello, sir. Am I audible?
Yeah, you're audible.
Yeah. Thank you for a very interesting talk. Especially, I'm really happy to see you're talking about random geodesics, which perhaps I saw for the first time. So my question was somewhat because you discussed there is a classical geodesic and now you're discussing
Yeah,
random geodesics and somewhat
that's right.
relating it to define a new sort of random geometry.
That's right.
So there are a lot of results and available in classical geometry about geodesics. So
Yeah.
can we expect this random
Ah,
geodesic to behave similarly? And you
okay.
carry forward those things to
I see.
characterize nature, which is more random.
Yeah. Okay. So here is the point.
I think
So
partially you
every
answered, sir. Somewhere in the later part of your talk, partially you answered when you showed that result towards the end.
Yeah, that's right. So let me sort of try to parse that question a little bit. Anytime you ask a question about this, then the much of the work really goes into, I mean, the first bit of the work really goes into formulating this stuff in a precise sense. So here is what can be expected. Firstly, I mean, in hyperbolic geometry, triangles are delta thin. The question that could be basically that, well, in the random geometry, are triangles all delta thin? The answer will be obviously no, because there will be a probability measure you will be, or I mean, lengths that you will be able to assign so that you have fatter and fatter triangles. It's a probability zero event, but you can construct a particular triangle even in an underlying graph or whatever. I mean, slightly. I mean, if you exclude this tree, you will be able to construct triangles which are fat, arbitrarily fat, a sequence of triangles which are fat. The right thing then to ask is, well, on an average, can you recover that triangles are thin? That's a good question. And I suspect I've not really worked on this, but we've not really worked it out. But I suspect that yes, in some distributional sense, I mean, essentially, if you look at the fatness of triangles, then, and if you fix a particular triangle, say, then the answer will be yes. On an average, any fixed triangle will be now delta of, as a now of a function of omega thin. So yes, and then you can ask finer questions. Well, okay, fine. Can you average this fellow out and you get a finite number? And I'm pretty sure that the answer to that will be yes. So it all depends on what probabilistic lens you're really looking at this question from. And one way to formulate it would be, can you make this thin or hyperbolic on an average precise? And I think in several particular cases, the answer is yes. That's one thing. However, and here is one particular thing which I did not talk about. So this is one place where random geodesics are behaving like deterministic geodesics. So there are two things. I mean, essentially all the questions in the area really boil down to the question you asked. So the first thing that we talked about is that random geodesics have a direction, right? So a deterministic geodesic always has a direction, is a tautology. It's not a tautology for the probabilistic thing. So the first property that we identified, it says that yes, random geodesics do have a direction. One. Second, we also pointed out it has, I mean, the deterministic geodesic has velocity 1 by definition, but it's not a given in the random case. So there also, what we did was we actually proved that the random geodesic does have a velocity. Yeah. So yeah, so both these properties that we outlined did say that some features of deterministic geometry are reflected in the random geometric world. However, in some cases, the random geometry gives you more. And this is something I did not quite come to. So in this case, but I did give you one example of this Z with plus minus 1, plus minus 2 as generators. And you look at the plus infinity direction, there are actually infinitely many geodesics which go towards plus infinity. Which are they? just take 0, 2, 4, 6, 8 and go straight out via even numbers. That's a geodesic going off to plus infinity. Or you could do 0, jump up to 1 that's connected by an edge, and then follow all the odd numbers 1, 3, 5, 7, 9, etc., etc. That also goes off to infinity. So you have these two fellows which track each other, which are at distance one from each other, and all of them go off to infinity, which means that geodesics going off to the same direction plus infinity stay in a bounded neighborhood of each other, but they are not unique, right? In the deterministic world. That is a probability 0 event in the random world. Why? Because essentially, if you have two paths and you allow your probability measure to be continuous, for two given paths to have the same length is a probability 0 event. I mean, essentially, it's what are you saying? You're solving an equation where you have random variables. The first one has edges E1, E2, dot, dot, EK. The second path has edges F1, F2, dot, dot, FM. They might be, M and K need not be the same. Yeah. But these two edge paths, now you are assigned weights. So you have W1, W2, dot, dot, WK, and you have V1, V2, dot, VM. So what are you solving for? You're asking that V1 plus dot, dot, plus VM is equal to W1 plus dot, dot, plus WK. That's an equation, right? So it's an equation. An equation is going to always cut out a codimension 1 space, which has 0 measure, right? In Rn, yeah, any codimension 1 plane has 0 measure. So it's a probability 0 event that two edges have the same length. So in the random world, this non-uniqueness of geodesics does not happen. It's a very rare event. And so you do have uniqueness. Yeah. So that's something that is very special. I mean, that's again something that is different from the deterministic world. So the answer has two sides. One, where deterministic properties of the geometry do go through, and one where you have actually more interesting phenomena. You have something richer, some structure which is not typically expected in the deterministic world, which suddenly emerges in the random world. Does that address the question, Aklak?
Well, I think so, Mahan. I'm not sure because participants have to be unmuted each time, so you may not be able to respond directly.
Okay, fine.
Yeah. There's a question from Gina. Are we moving away from an absolutist view of measure to a more probabilistic view of measure or geometry?
This is philosophy. It's outside my domain, really. So, I mean, yeah. So, yeah, I prefer to pass that. I mean, yeah.
Yeah. Okay, Jam, you also wanted to ask something.
Yeah. Jam had a question which was very interesting. It was.
You may want to add something to it also.
Yeah, Jam, go ahead. I did start off by saying something. Do you want to add to that?
Can the host unmute Jam in case he's muted?
Okay. Okay. Mahan,
Jam, you can also unmute your video. I mean, the horrible thing about this.
I think the host has to make me unmute. Yeah.
Oh, okay. Yeah, great.
But anyway, yeah. So I had this question earlier, but I have a couple of more to add. I don't know.
Ashish, will you make him co-host? I'm not host.
It's okay. Don't worry. Yeah. So,
no, it's okay.
So what I wanted to ask was about the global geometry, so to speak. I mean, in the sense that is the geometry random at every scale? When you said fractal, that's what I understood. But would that depend on the generating set, or is it general? Also, I had kind of assumed that the fluctuations would kind of even out.
So that's the kind of stuff that one would like to prove in most cases. And so here's the thing. I mean, many physicists really make they sort of rely in many computations for the different fluctuations that are nearby cancelling off, and so up to some order, the behavior is like, say, some x. So here is one other completely, I mean, this is why, I mean, you had asked for what is a kind of a visual thing.
Right.
And here is my answer to that. I mean, what does a typical fellow look like? And this, I am going to go to a different model of random geometry, which is something that is really, I mean, when one talks about random geometry nowadays, this other model is something that is very much in the, it's a hot area. Yeah, and yeah, okay. So I think just to sort of suggest to any enterprising young people in the audience, this is stuff that there's a theme towards which all of this, I mean, all of this stuff is centered around. And it's actually one of the 7 millennium problems, right? So there is this problem which was posed in the year 2000 or 2001, namely saying, find a mathematically precise way of talking about quantum field theory. And really the physical problem, so I'll come back to this question of jams, but I'll just sort of give a bit of advertising spiel for the area. So there's this problem that was posed. So so basically it's the real problem is because the physicists use this incredibly powerful rabbit out of a hat called the Feynman path integral. And mathematicians have absolutely, well, not absolutely, but it's probably an overstatement, but we really have not much way to make sense of it. However, as soon as you discretize the problem and then look at this kind of a model, the kind of model that we've been talking about, then you're really, you're in a well-defined probability measure space, and integrating everything makes sense. It's not a path integral. You're not integrating over some huge infinite dimensional thing. You're just integrating over some finite dimensional thing or a limit of finite dimensional guys in some very precise sense. So this is one way to go around that problem. If you discretize and look at this graph, and you can address that problem. And so this part of the problem is, at least mathematically, it's completely well formulated. And of course, it takes work. But and then there's another completely different other aspect of the problem where you're going to allow the mesh size to shrink to 0 so that you can recover the continuum, right? But at least this discretization is something that can be addressed sensibly in traditional mathematical language. Coming back to your problem, I mean, how to visualize, how to see what this stuff is about. And here's the kind of model where you can and do make sense of the visual thing. Namely, take, say, a sphere, just an ordinary sphere. You triangulate it at random. Say you assign some number, again, say 10,000. So every vertex has valence bounded about by 10,000. Or even better, just don't assign anything. Just look at all triangulations. So basically decomposition of the sphere into triangles, where you keep some upper bound. That means, so for every capital N, say 10 million, you look at all possible triangulations of the sphere where the number of triangles is less than equal to, say, 10 million. Then the kinds of collection of triangulations that you get, you put the uniform probability measure. So it's now a probability measure on the space of triangulations of the sphere. One. How to make geometry out of it? Assign standard Euclidean equilateral triangles. So basically make all the triangles equilateral, normalize so that, say, the diameter is something fixed. Now let n tend to infinity. There's another model of random geometry. It's basically going to give you geometries on the sphere where the where each piece is a standard fellow we know and love, namely a small little equilateral triangle. And then what you get, you can actually start seeing these gadgets, and there are computer simulations. And so basically here are sort of names, you can sort of Google them. Legall, Legall, one of the people who got the, I think, the Wolf Prize or something like that couple of years back. He's one of the people who's the originator of this particular model, Le Gall and Miermont in France. And there are people nowadays who have been drawing pictures, and it looks like, typically one would expect, see, it's a sphere, so it's forced to sort of fold in on itself, and then it starts poking out various limbs. And really, this is, it's sort of very constrained development. Unlike the tree, which is allowed to really grow outwards, here it's because the whole ambient space is fixed to be a sphere. There are sort of limbs growing out, and then they try to branch off a little bit, but the ambient sphere sort of tries to pull them back. It looks quite crazy, and it looks like a fractal. And it is true. The Hausdorff dimension of that is typically going to be larger. It's going to be 4.
Mahan and Jam, I'm sorry, I have to stop this because the GBM needs to start.
Yeah, absolutely.
We can't start that unless we stop this session.
Yeah, absolutely.
Okay. Yeah. So, all right, so let me wind up. 1 or 2 questions were left, but maybe they can be taken up through some other medium. Thank you again, Mahan, for really a very fascinating talk, and all the your responses in the Q&A also, added so many features to things. Those people here who are MTA members, we will be starting the GBM now. That has a different link, so you will need to log out of this meeting and join us at the separate link. We look forward to see you there, and otherwise we have our afternoon program, of course, later, and you can look that up, and we hope to see you there as well.
Bye-bye.